Today we're doing our demonstration on EM waves, or electromagnetic waves. Guy here is gonna hit this ball right here into this the line of pool balls, cue balls, or whatever they're called. It's gonna hit. He's gonna send a vibration all the way through to the end one, just like an EM wave transverses through matter. Wow. The negative end and the positive end. But when you split it in half, it's supposed to stay to a line. But now, all the negative over here, or positive over here, and the negative over here. But that's not how magnets work. When you split it in half, this becomes the new pole, also over here. So now there are two North Poles. So now it's the North Pole and the South Pole, and the North Pole and the South Pole, instead of North Pole and the South Pole.
Okay, so the anatomy of the wave, for the highest point of the wave, you have the crest, which we represented right here. It's the highest point from the midpoint. And then the distance in between each crest of the wave is referred to as the wavelength. And then towards the bottom, at the bottom of the wave, is the trough, the lowest point, and then the height between the midline and the top of the crest is called the amplitude.
So we're going to talk about dipoles now. Dipoles are poles that are equal and opposite, and they're
Really? Need to restart.
equal and opposite magnetized poles separated by a small distance. And magnetic field lines are visually describe the influence of magnetic forces in a region. They are describe the direction of the magnetic force going from north to south. So they go here at north, and they go, and then when they go a little bit farther, they go, and then they go even farther, like. So now we're going to talk about magnetic flux, which is a measurement of how much of a magnetic field passes through an area. It's useful for helping describe the effects of the magnetic force on something occupying an area. The measurement of magnetic flux is tied to that same chosen area. Now, for magnetic domains. They are regions in a magnetic material where magnetization is in a uniform direction, such as these cue balls, all traveling in the same direction.
Okay, so there are many different types of waves. The first type of wave is a transverse wave, which is a wave that oscillates perpendicularly in the way it moves, which is like that, just moves that way. And then the next type of wave is a mechanical wave, which is a wave that requires a medium to be able to transfer energy and to be able to move properly. And the next type is a matter wave, which is the essential part of the quantum mechanics, which is like the center of most waves. And the next type of wave is a surface wave, which is a where the particles of the medium undergo a cylindrical path. And then the last type of wave is a compression or a longitudinal wave, which is a wave where it just refracts on each other and compresses.
Okay, so now we're demonstrating the ferromagnetic fields. So at first, unmagnetized, it'll be sort of crazy, semi-organized like this. But then when you magnetize it, it becomes organized and very strong. And you do not need magnetic fields for a ferromagnetic. They last a very long time, like iron. Iron is an example of ferromagnetic. Paramagnetic is the complete opposite. It's crazy, and it's very weak and does not last a long time. It's temporary. But when you magnetize it, it becomes a lot more organized. But again, it's weaker. It pops open, unlike ferromagnetic. That is those things.
Today, we're going to be talking about the EM spectrum. It's a range of all electromagnetic waves, from radio waves, to microwaves, to infrared waves, to visible light, to X-rays, to ultraviolet light, to X-rays, and to gamma rays. And radio waves have the longest, that's why they're all over here. That's why they're all the way over here. And then gamma rays have the shortest, so that's why they're all right here, almost touching. Gamma rays and radio waves are produced in the same way, in different ways, but are still electromagnetic waves. Electromagnetic radiation, aka protons. The more energy, the shorter the wavelength, which creates the EM. EM radiation is based on 3 measurements. Frequency, aka hertz or cycles per second. Wavelength, also meters, measured in meters. And energy, measured in electron volts.